So we have completed our critical theory sections for recurrent neural network, and I also introduced the LSTM model, GRU model, and other kind of advanced RNN models and their architectures. Now in this lab session, we are going to start from the last session where we ended. We are starting from that convolution network. We'll perform the same task to classify the sentiment categories for IMDb movie reviews, and I have opened the previously completed convolution neural network notebook. I'm going to create one new copy of it. We will have very minimum amount of change to implement these new approaches, whatever we discuss. What we are going to do, first we are going to implement simple RNN or recurrent neural network. Then we'll take one step gradually toward the advanced models. From simple RNN to we'll start with the LSTM model. Then we'll also try GRU model, gated recurrent unit, and then we'll try bidirectional LSTM model, and then we'll try the stacked bidirectional LSTM model. So all these models will take a little bit of time to implement, especially the training sections. So let's jump in straightforward to see like what kind of performance we are going to get. One thing for our note that we already have got around 95% accuracy in our predictions for the sentiment classifications. We'll target to cross it. So what I'm going to do, I'm going to create a copy of this notebook. We are going to implement a simple RNN model first. So I'm going to give a name to sentiment classifier with simple RNN. I'm making a demo. So the first step itself, we need to include the required packages for this particular type of model. So as we are not going to use any kind of convolution layer here, so I'm just taking the special dropout in the previous line itself, and I'm going to drop this particular packages. We don't need them anymore. So what do we need to call? Simple. Alright, so okay, so let me comment these sections. Let me import it first, then it will be easier for I will quickly go through all these required packages for now also, so that you can kind of you don't need to go back to the previous sessions to find out if there is anything missing. Alright, so import is done, and so what do we need to do? Alright, so we are importing Keras, and we have imported here the IMDb dataset. Now this is one of the kind of backbone function we need, that is the pad sequence. This is the kind of Keras natural language pre-processing methods which will help us to kind of truncate or to pad the movie review content. So in case the movie review size is bigger than our specified hyperparameter, then it will truncate truncate the content, or if it is smaller than the required size, then it will add zeros in front of the movie review, so that every reviews will have the same length. We are going to use a sequential model in this particular case. Now we have dense layer here, we have flattened layer, we have dropout layer, we have embedding layer, we have spatial dropout layer. Spatial dropout layer is specially designed for dropout on embedding layer. These embedding layers will help us to create a word-wake model, word-to-wake model. That means distributing those each and every words on the basis of their meaning and semantics, on the meaning and their kind of significance in a higher dimensional vector space. And then we are going to use those higher dimensional representations of those words to classify our to feed into the RNN layers, recurrent neural network layers. From there, we are going to feed the content to the output layer to predict the positive and negative sentiment. We are using simple RNN neurons or network, so that's why we are importing this particular type of layer. It's called simple RNN. Okay, so we are going to use a checkpoint function so that we can keep track of any intermediate, any kind of particular epoch. Whichever epoch provides the higher validation accuracy, we are going to use the weights from that particular epoch. We are going to use ROC AUC, that means receiver operator characteristics, as our measurement or accuracy measurement or performance measurement parameters. We have some uses for the pandas data frame, and we are going to visualize the output for our quick analysis. So that's why I'm importing all these required components. So in this particular sections, we are having the hyperparameters. I'm going to create a new folder for this particular type of modeling. So let me give a quick name, maybe simple RNN. Oops, sorry. All right. So we are going to execute for 4 epochs here. We are going to take the batch size of 128. We'll represent the each and every words in a 64 dimensional vector space. These are the parameters for our embedding layers. We'll have the total number of 5,000 unique words in our complete review data content. We are going to skip top 50 frequent words. We are going to have a movie review length of 200. Let's start with the smaller one because this RNN we're going to take a bit longer time to execute. We are going to have 2% embedding dropout, and we are going to have a padding and truncating from the beginning of the each and every movie review. That's why I'm specifying it pre here. These are the convolution layer specific parameters. We don't need them anymore. These are the dense network. Again, we don't need them here because our layers will have directly the RNN sections. So we are going to specify 2 more hyperparameters here. One is n number of RNN. That would be I'm taking 256 here, and we need to have RNN dropout as well. Drop RNN equal to, I'm going to take 2% again. So that should be sufficient for our hyperparameter sections. Now I'm going to load the content in our X-train and Y-train, X-test and Y-test dataset. And so these X-test and Y-test are basically the validation data, and X-train and Y-train are the dataset which we are going to use to train our model. So here a quick review for the dataset size. We have 25,000 each for the training and test dataset. Here's the quick indexing operations we are doing, and we are going to add padding at the 0 index and start is the index 1 and unknown character as index 2. So all these things I already explained while creating this initial dataset for that convolution neural network. If you want, you can quickly open that thing also for your side-by-side review. In this particular sections, we are primarily going to focus on the performance and the process, how to create the model for simple RNN. So to do that thing, I'm just executing all these steps, and in this particular cell we are going to do the pre-processing operation using the pad sequence functions. We have several parameters here which I have passed, like truncating is the pre, and padding is also pre, and max movie length is max length basically is whatever hyperparameter we have specified here. It's just 200. So it may take bit longer time. Okay, it's done. It's a few seconds. Now in this particular network architecture, we need to define the required layers for the simple RNN as well. So as we already discussed, we are not going to use any convolution layer here, and dropout layer I'm just going to drop them. So I'm adding that simple RNN layer. Alright, it's not coming. Okay, I don't see any reason for not coming here. Okay, I hope I imported this thing. Okay, so in this particular section, once we have first layer, we have embedding layer, then we have spatial dropout layer, and then we are going to use that simple RNN section. We need to specify the number of neurons in these alright, now we are going to specify the dropout as well. Dropout equal to drop RNN. So our model architecture is ready, and these RNN layers will feed to the directly to the output layer. We are not going to use any kind of dense layer after this. So if you want, you can play with this architecture. You can add additional kind of models and additional kind of layers here and there. So I'm sure you will have fun while doing that. Okay, so I'm just let's see the model summary here. So we can see that total number of parameters are almost 0.5 million, like 400,000 parameters are there, and embedding layer will have these 64 dimensions for that each and every word of total 200 possible combinations, that in input length or input neuron size, what I'm talking like. Okay, that embedding layer will have these 300,000 parameters, and these RNN will have these 82,000 parameters, and the output layer will have 257 parameters. Okay, so let's compile the model. We are going to use the binary cross entropy, as we'll have only one output, which will be kind of binary kind of output, either 0 or 1, and we are going to use that Adam optimizer and accuracy as our performance measurement metric. So let's execute this particular step. Now I'm going to create the directory where I'm going to save the model weights or weights from each and every epoch. Alright, so here I'm defining the checkpoints. Now I'm going to execute this model. So this particular model is going to take a bit longer time to execute, and compared to the like whatever we have, it's a 400 seconds each and every execution. So let me execute it, and then we are going to So it is expecting around 164 seconds to complete. So if you're running in a GPU mode, it should not take more than 1 minute or maybe 30 seconds. I'm running it in a CPU mode, so it is going to take that much time, around 2 minutes or 3 minutes every epoch. So let's wait for the time. In the meantime, what I can show when it is being trained, I already have executed these models, and I can show you the what kind of performance we are going to get. Uh, Alright, so this is the model, simple RNN demo, which I already trained, and I executed that in a CPU mode. It took around 80 seconds each execution, so we got around validation accuracy for the second layer itself. It's a 0.80% validation accuracy, and these are kind of mean square error sort of things. So finally, up to the predictions, we can see the predicted class distributions are not that much good. Majority of them were predicted as positive sentiment, and few of them were predicted as negative, but for negative sentiment the confidence was very less, where they confidently told like it's a 0, and we got overall ROC AUC as 88%, which is pretty low, pretty lower than whatever we got from convolution layer. Okay, so once this model is executed, you can perform this operation as well. Like you can try to pick up the best performing epoch weights, and you can predict the test content, and you can present it here. So I would highly recommend you to play with the different hyperparameters, like increase the review length, or number of unique words, or you can drop this particular content also without skipping any word, or increasing the RNN size. All these sort of things you can play with that, and you can uh, try to get as much accuracy as you can. Alright, so we have minds to go. So what I'm going to do, I'm going to skip this particular section, and I'm not going to come back to these simple RNN anymore, and we are going to jump into our next section. What we are going to do there, we are going to create a LSTM model, basically simple and single layer LSTM model, and let's jump in. Let's see like how it works and how to create that thing. Okay, I'm just waiting for this to complete one epoch, and then I will terminate it and I will jump into the next section. Alright, so I'm done with this training, so I'm just closing it. Alright. Okay. So we don't need these anymore. What I need to do, most importantly, I need to shut down few of them. Alright. So what we're going to do next, we're going to copy the same notebook and we are going to implement our LSTM model here. Okay. Alright, I'm giving a good name to it. I'm going to make it LSTM model. Alright, so what we need to do, and the simple RNN model itself, we need to call LSTM. Let me import the content first. Alright, so I'm going to import LSTM here, long short-term memory. So rest of the content should be as is. So I'm just calling this LSTM content. Additionally, LSTM layer. Now we have to specify some more hyperparameters here, or we have to tune the hyperparameters a little bit. And I'm going to name the output folder as LSTM. I'm going to keep the unique word as is, and the length of movie review, let's make it 400. Okay, rest of the things should be fine. In the place of RNN, if you want, you can use LSTM also, so kind of things. And so pretty much we are going to keep it. We are going to do the data load. We are going to do that indexing and all sort of things. We'll perform the pre-processing operations. It is done. Now we will design the network architecture. So it is straight and simple that you need to call this LSTM function here, and the number of modules inside LSTM will be same whatever we have defined as hyperparameter above, and the dropout content will also have the same. Okay, nothing special required in this particular section. So our model has been created and number of parameters got increased a little bit. You can see it here, it's now 600,000. Okay, so maybe we can proceed further with the model compilations. We are going to compile the model. We are going to do the output directories. We have created it. Now we are defining the checkpoints. Now in this particular sections, we have the training process. If we hit it, it is going to take a bit longer time. So you can execute it and you can wait for some time, and till the time it's getting trained. Normally in your GPU mode it may take somewhere around 300 to 400 seconds each and every epoch, and in CPU mode it may take a bit longer time. So make sure that you have some time in your hand while training these models, and along with that you have to play with the different hyperparameters going forward. But what I'm going to do, I have some already pre-trained models, so I'm going to load few of them in our training. So what I'm going to do, I'm going to use one of the pre-trained content here. So let me load it. Alright, so let me have a quick look into the this is what currently we are working on, model output here we have LSTM. I'm going to pick this particular model. So it is saying something. Let me listen to it. What is this one? This is what I don't need anymore. All right. Okay, so what I did some discrepancies in the hyperparameter itself. Then whatever I have trained those models on. And so let me do a quick. All right, so model has been loaded now. And so this training process will take around 300 to 400 seconds each epoch. So I have loaded the models already. Now let's see the prediction process. So I'm storing all the predicted values in the y hat variables here. So it will take a bit longer time. So bear with me for some time. So even the training, even the prediction process will take time depending on the complexity of the model. So pretty much this is our previous best figures. So almost more than 50% done. 40 more seconds. All right, so our predictions are completed now. Okay, here you can see we have pretty much confidence on the higher positive sentiments and negative sentiments, and in between we have some values, but those are quantities are very less. Let's see, like from an EUC point of view, how we did. Okay. So we got 94.5%. It's a pretty good result. But still we are far behind that 95% benchmark whatever we have said using convolution there. But I'm sure that if you play with these different hyperparameters, we can come very close to that. And you might be surprising that why LSTM is performing kind of bad performance over that convolution network. For LSTM, we need to have a decent amount of training data. Compared to that, these IMDb movie review database contains less number of training records. So if you are getting sufficient training data for any kind of implementations and projects, you can try with this LSTM model. It is going to perform uh, in a much better way than anything else. Definitely you have to consider the hyperparameters while doing the training or designing the model. So we are not going to stop here. We are going to jump into our next model. That would be bidirectional LSTM model. Or before that, let me try with the okay, let's go to bidirectional LSTM model. Okay, so what I'm going to do, I'm going to create a copy of it. I'm going to give a good name to it. Bidirectional LSTM model basically considers the the previous set of sentences and or words, or the successors or the next set of sentences or words, while uh, deciding the the value of that content or current context word. So that's why it is called bidirectional. So in this particular case, what we are going to do, we need to have something called one wrapper. It's called bidirectional wrapper. What it does, it okay, so we have this LSTM here. I'm not disturbing it, and we are going to call the wrapper here from keras dot layers dot wrapper import bidirectional. That's all. Dependency point of view, that should be all. So here what we are going to do, we are going to do minor change. The batch size is as is, and we are going to reduce the movie review length to 200, basically 200 left side and 200 right side. So total size is constant, like total size is 400. Now we are going to load our data. We're going to do it very fast. We're going to do our pre-processing here. Now this is the kind of content where we are going to implement the bidirectional LSTM model. What we have to do, okay, so you just have to place the wrapper the both side of this LSTM model. I don't think there would be any other parameters needed for this bidirectional content. It should be sufficient. And alright, so that's done. Okay, so our model architecture is ready, and similar to this, we are going to create the directory. We are going to do the model checkpoint. Again, I'm not going to train this model in this particular session. I already have executed the training process, and I have the training models saved somewhere, but for you, you can execute this training line also. And okay, so by LSTM. So what I'm going to do, out of those trained content, I have, as far as I can recall, the first epoch itself produced the higher accuracy. So here one thing I forgot, like I forgot to change the model output name, output directory name. So this is 0 index. The first epoch itself produced the higher accuracy. So you can complete the training here, then you can pick up whatever um, base epoch you are getting on the basis of that validation accuracy. So I'm going to load the model. I hope it will be fine. Okay, it was loaded fine. So this particular load also, this particular model prediction is also going to take a bit longer time. So bear with me, and then we'll see whether uh, we are able to cross our previous best figure is 94.5%, or we are going to perform lower than that. So 2 more minutes to load. Right, 50 more seconds. Yeah, almost done. All right. So we can see little bit of shift happened. Like earlier we had higher number of positive and negative was almost balanced. Now we have higher number of negative sentiments. So let's see the AUC values now. It got reduced around 0.5%. So currently this bidirectional LSTM is producing around 94% accuracy. So again, as I told, like you can play with these hyperparameters, and I will also recommend you to find out all the movie reviews where we have uh, misclassified those contents. Uh, in this particular session, I'm just trying to show you like how to implement those different kind of models. Next thing I'm going to jump in is something called stacked bidirectional LSTM model. It's another layer. So what we can do, the dependency point of view, we don't need anything else. So we have pretty much everything. So let me copy this notebook, maybe copy, and so let me give a good name. Stacked bidirectional LSTM model. Don't get scared. Stack is nothing but like multiple layers of LSTM sequenced together, sequenced in a sequential way. And one important thing, like while designing the architecture, so I will explain. Okay. So here I'm changing the name of the folder as well, so that we can save those stacked models. Okay, let me copy the folder name from here, it would be easier. stacked by LSTM. Alright, so it's inconsistent. Rest of the content should be as is. I'm not going to change anything. So let it be. And I'm going to repeat this same content for 2 times. Here I'm doing the pre-processing. Now this is the design section. Alright, so one important thing is that we have to specify that the first LSTM layers returning the hidden outputs sequentially. Okay, so there is some parameter which is known as, it's supposed to be return sequence or something like that. Dropout return okay, return sequences is equal to true. That means it is going to feed the step-by-step output to the next layer. Let me check. Okay, it worked fine. So here we have two LSTM models, two bidirectional LSTM layers. So that's why it is called stacked LSTM model. Alright, so here's the model compilations and rest of the things. You can execute the training process as well, and it is going to take a good amount of time. Like for me it took around 1000 seconds. With the GPU executions it may take a bit longer time for you, or maybe if you have more powerful GPU then it will take a little less time. So what I'm going to do, I'm going to, as I remember, the first epoch, the second epoch basically contains the highest validations accuracy. I'm trying to load it, okay, and I have loaded it successfully. Good. And next I'm going to do the predictions. Predictions is also going to take a bit longer time, okay, 300 seconds in this particular case. So alright, so I will just fast forward this content and then we'll see it, like whether we are able to achieve any better result or not. Once this section is done, I will just quickly show. I will suggest few of the changes which you can try yourself for the modeling approaches, and then you can find out the result and you can compare your own findings. Yeah. Uh, if you are struggling anywhere to implement any particular section of the code, you can come back anytime and you can redo this video. And I will recommend all the time, just try to see it first and then try to implement by your own, and then you will understand. You will face several challenges and you will also understand some very critical components and very quickly. So, and the best thing is that you need to play with these hyperparameters and this model architecture and everything, all the possible things, and certainly that will help you to kind of understand this whole uh, these RNN and this natural language processing contents in a much better way. So let's wait for these prediction process to complete. So we have 120 seconds to go. Hundred seconds more. Alright, so training is done. Basically the prediction is done. So let's see how it did. Alright, it shifted once again. So we can see that higher number of positive predictions and lower number of negative predictions. So let's see our AUC values. Okay, didn't improve too much, but if we train it for sufficient epochs, and we can be a bit luckier than this, and you can play with these hyperparameters once again, depending on your infrastructure, whatever you have, and however it permits. Okay, so before I wrap up for these quick lab sessions, few suggestions and few modeling suggestions for your homework. You can implement GRU, gated recurrent unit, whatever we have learned in the previous theory sections in the last content. You just have to call this GRU layer, and you have to specify the GRU layers while defining the architecture. Okay. Along with that, you can have a convolution and LSTM, bidirectional LSTM stack layer. Okay. So basically, from you will have one convolution layer, and then followed by one LSTM layer. I'm sure that is going to give the best result, because you already have proven that LSTM is going to produce higher validation accuracy. So you can try to implement that content as well. Okay, so in the next lab session, what I'm going to do, I'm going to show another kind of modeling approach rather than the sequential approach. We'll have a functional model where we have kind of couple of parallel model architectures will come and will be concatenated and to produce some of the output. So alright, then see you in the next lab session. And in this particular sessions, you have lots of homework to do. You can play with the different modeling suggestions, whatever I give and whatever I did here. You can train your own model, and you can come back anytime if you are struggling anywhere to uh, kind of to create the code and to train the model. You can leave your comments, like if you feel somewhere you need help, I will definitely clarify all those contents. All right, so